Okay, good. So I'm going to talk for roughly 15 minutes or so and then answer some questions about ZK Starks and StarkNet. So let's start with a little bit of, just reminding ourselves whence we came from. So there's a paradox with blockchain. Bitcoin is a pretty new technology. Ethereum is even newer. So why are they so slow in terms of the amount of transactions they can process, especially when you compare them to older payment systems around? Why is it? The answer is that the prevailing conventional system has a big advantage in which you're fine with trusting some big party, which can buy some big computer and then run at very high TPS, transactions per second. And if you ask yourself, okay, how do we trust the system? Well, you delegate accountability or the process of holding the system accountable to some accountants and lawyers and so on. Now, blockchains work very differently. They have a principle of inclusive accountability, which means that everyone must be invited and able to verify every aspect of the blockchain, every single transaction. So verify, don't trust. And because of that, you can't really just increase the number of transactions by a lot, because then people will start dropping out as their laptops are just not going to be able to hold up to the bandwidth. So because of that principle, blockchains, that's the answer to the paradox. But this inclusive accountability, this beautiful principle that is very much like direct democracy, sacrifices both scalability and also privacy. And cryptographic proofs, and there is a large family of different kinds, they can solve both kinds of problems. So what is it that proofs deliver, and what other technologies out there can deliver similar things? So really what you get from them is integrity. Proofs are a means to an end, and the end is integrity. So here's a beautiful story. The Empty Pot tells of a barren, childless Chinese emperor who wanted to pick his heir, and he devised this contest in which all children in the kingdom will come and receive a pot and a seed, and they must water the plant. And at the first day of on the first day of spring, they'll come, and the emperor will pick the one whose flower is the prettiest. So all children arrive on the first day of spring with beautiful flowers in their pots, but for one child who, like in the book, came with an empty pot. The end of the story is that child was elected as the heir to the emperor because unbeknownst to the participants, they were given barren seeds. And this is the only child who operated with integrity. So integrity, as C.S. Lewis defined it, is doing the right thing even when no one's watching. And computational integrity means, you would like someone to run a computation as if you were running it, to doing the right thing. And what we would like is to live in a world where computations that mean something, that carry, value, or can decide all kinds of things about our freedom, our property, are dealt with integrity, with computational integrity. And there are right now 5 different kinds of technologies that can deliver integrity by very different means. And here's a very brief and maybe daunting, I'll share the slides so you can look at them a bit later in terms of a few parameters as they would appear on a blockchain. So the first technology that gives you integrity is the one that blockchains use right now, and that's naive replay, which means every node is going to run all of the, each and every transaction and check and update the state for everything. So you lose privacy. You have a pretty large off-chain footprint for all the data that you need in order to verify signatures and so on. But it's extremely resilient and secure. Basically, the cost of stealing something is pretty much infinity, because any node on the system can just see if something bad happened, and if the system gets broken, everyone just knows what happens and can fix it. So that's one way. Another is delegated accountability, which is this very old method, the one that banks used. use. They have very good privacy because only the bank knows what's going on. They have pretty good scalability because one computer can carry all of the weight. If you put them even something like this on a blockchain, and there are such things such as side chains and these creatures where you basically trust a single node. Centralized exchanges are like that. You're trusting a single operator to do the right thing. They have very small on-chain footprint, but they are, you only need to bribe essentially one person in order to steal the funds there. There is a hardware solution, the trusted execution environment, that promises good integrity. It also has very good privacy and very small on-chain footprint. But again, you can just basically get one key for one of these hardware, thingies like SGX, and then the system is compromised. There are validity proofs that rely on cryptographic proofs, such as Stark, Snarks, and similar things. There you get very good privacy. Scalability is very good. The on-chain footprint is slightly larger than other things, but negligibly so. And since practically speaking, there's no way to really break a good, well-designed zero-knowledge technology, the cost of theft is again infinity. And you have fraud proofs, also known as optimistic rollups, that don't have privacy, have somewhat, I'd say, medium range scalability, because you do need to put a lot of stuff on the main chain, and you do need a large set of auditors to basically replay all of the transactions. And the on-chain footprint is not so good. And there's a small set of contenders that you might bribe and break the system. So anyways, what the L2 that we're building is based on validity proofs, in particular on a Stark rollup or a validity rollup. So let's talk a little bit about the particular technology. So what is a ZK Stark? It's a proof that gives you computational integrity. So it basically proves that something is correct. Here's an example of some proof of integrity. This is a receipt from a restaurant. It proves to you that you're supposed to pay $89.50. The prover would be the restaurant owner. The verifier is going to be the customer, which is you. And the way you're going to verify it is probably by re-executing the same computation and checking that you ended up with the same sum. ZK Starks give you some form of receipts, but they're like some receipts. All these zero-knowledge proofs and succinct proofs are some kind of receipts on steroids. They deliver the same thing, which is integrity, but allow you to shield some of the inputs. That's the zero-knowledge property. They are scalable. Some of them are. Starks are. You have exponentially small verifier running time, while the prover time is nearly linear. Just one second. Sorry, I'm at home. Sorry. That's when you Zoom from home. Okay, they are universal, applied to general computation. Starks, the T in the acronym Stark stands for transparency, which means that all verifier messages are public coins. So there's no trusted setup and no toxic waste, no trapdoors associated with them. And the particular Starks that we're building also use lean and battle hardened cryptography, which is also post-quantum secure and relies only on the existence of a collision resistant hash function. So this is some theoretical work that I've been doing for more than 20 years, and but now it's also a very practical matter. So the way we use it currently on blockchains is that, sorry, I have some things that okay. The way we use it on blockchains is that we basically have a prover running off-chain. The prover is processing a very large number of transactions and generates proof and sends it to a verifier. So instead of the current situation where each node must process each and every transaction on the blockchain, if you think about Ethereum, and you also need to update the storage with the state of the system constantly. Instead of that, we're going to ask the nodes of the blockchain to run a verifier and basically update some root of the new state of the system as long as it's accompanied with a Stark proof. And this is the way that our systems are working. So now what the blockchain is doing is merely verifying proofs, which are exponentially smaller than the amount of computation they attest for. And you still have the same computational integrity as you had previously. So let's see what these things are doing in the wild these days. So Starkware, the company I co-founded about 4 years ago, has two main products out there. It has StarkX, which is really the largest L2 by TPS by a pretty large margin. The numbers here are already not exactly correct. Right now we're running at a TPS that is actually, meaning at a rate or a number of transactions per second, that is actually higher than Ethereum's. This is of the past few days. And we have, coming within roughly a month and a half, we're going to have the mainnet launch for StarkNet, which is going to be a permissionless layer 2, on which you're all invited to start building. You can already start building on it today, and many are doing that thing exactly. So Starkware is a company that whose pedigree includes inventions like ZK Starks, Fry, Cairo, the programming language, shared proving, Validium as a data availability solution, and Volition, and a bunch of other things. Our mission is to bring scalability and privacy to a blockchain near you. As I said, we have roughly 2 products, roughly 50 team members, and we got some considerable funding in the past. Here are some numbers about StarkX, which is running for more than a year. The cumulative trading by now is already over $50 billion. We settled over, I guess, 25 million transactions, 100,000 users. We're minting NFTs at a pretty large rate. We just tweeted that tomorrow casually we'll be minting another 500,000 after we minted 3 million over the past weekend. And the gas per transaction today, as measured across our different systems, is less than 1,000 gas per transaction, even though these are pretty complicated transactions. We're servicing DYDX, whose volume is like shooting up to the moon. As of now, it's more than $7 billion of 24-hour volume at a rate of 10 TPS, all of it working on our system using Starks, Sorare, that does fantasy sports, Immutable, they're a gaming company for NFTs, and Diversify spot trading. Yeah, the transactions per week are constantly increasing, and it's hard to keep track of how much of a sort of growth we're seeing there. Again, these are graphs from about a week ago. They're not updated. We are at a TPS that is now nearing that of Ethereum, and our transactions are more complicated. And that's about StarkX. Now, StarkNet is basically taking the same technology stack that we have, and basically allowing all of you guys to start deploying your applications on it. And as I said, this is going to be live in roughly a month and a half, but you can start building right now. And later on, we're going to decentralize the provers and the sequencers. That's going to take roughly another year, maybe a little bit less from the launch. But you can start writing your apps and deploying them within a month and a half, and you can already do so on testnet. So what do we have already now? On our testnet, you have general computation written in the programming language that we invented called Cairo. You have L1 and L2 interactions already there. You can permissionlessly deploy contracts and transactions. You have composability between contracts, and very soon, and certainly before the launch of this mainnet, you'll have ERC20 contracts. You'll have bridges between layer 1 and layer 2 and account contracts. The QR code here will lead you to StarkNet landing page, and you can start building and implementing. We have a very quickly growing ecosystem. We have 2 full nodes being developed by Fermion and by Equilibrium. There's a compiler that's going to be ready by the time we launch between Solidity and Cairo. It's going to be pretty efficient. There's already a block explorer. There are a bunch of other compilers, and the contract standardization is being written by OpenZeppelin, who also standardized Ethereum. So Cairo is a programming language in which all of our systems are written, and in which StarkNet is written. So it's sort of the C to the operating system that would be Linux. In our case, Cairo is like the C, and the operating system is going to be StarkNet. And it's a minimalistic programming language, but it's powerful enough to power all of our systems and also yours. So you should start playing with it. There's a very extensive tool set for it, compiler, virtual machine, extensions, tracers, and all of our code is already open sourced, including for DYDX and Sorare. All of these systems are open source, so you can use stuff from there. Here is a link with further resources, and with the few minutes I have, I'm happy to answer any questions.
Also, we have time for one question, since you're not going to be here for the panel. There's two in the Q&A. I can read the first one by Denise's. I hope I pronounced that right. It's always hard. He said, in the chart displayed by Eli, the theft cost was marked as infinite for Stark and for the layer 1 chain. The semantics of this is to create transactions, spending money that was never yours, but does not account for a common prefix violation where you double spend, correct? Oh, you're muted at the moment. Sorry, we can't hear you.
Sorry, I guess when you share your screen, you're supposed to say that you don't want to share the tab audio. So okay, I'm going to share again. Here we go. Can you hear me now?
Yep.
So what I said is that I do not. Can you repeat the question, because I didn't quite understand it, or maybe if you can explain it in your words, the question.
So basically, he says the theft cost is marked infinite for Starks, and he says the semantics is for this is creating transactions to spend money that's never yours, but does not account for a common prefix violation where you double spend. So I think what he means is if there's a fork, can you double spend? Is that right, Denise? Is that the best way to explain it?
But I guess StarkNet is a layer 2, so I don't know what a fork would mean. I don't think you can't have a fork, right? I mean, for that you need to fork, period.
Oh, here he is now. He can explain it.
Oh, okay.
Yeah, hi Eli. Yeah, I was wondering. First of all, in the naive replay solution, there you have a theft cost of infinity, and that's a chain, right? And there you can have a fork on the chain. But then also in the Stark case, you have these commitments where they come along, right? But then on the zero knowledge of what has happened. But what if I double spend and then the prover proves both that the first transaction is valid and then the second one is valid, but then it commits it to the underlying chain in two different forks? That will be an attack, and the cost of that attack would not be infinite because it just takes the cost of forking the underlying chain. So it would be large, but not infinite.
Okay, so yeah, I agree that forking, yes, it does reduce, basically it reduces to the security of the L1. So right, if you can fork the L1, then definitely you can do a double spend on that, or you can fork, right? But okay, I mean, infinite is not really infinite. It means very, very high. Also for L1, right? There's with naive replay, I guess it's something so catastrophic. What I mean is that everyone notices it, and because again, like suppose some really, really powerful nation state comes and buys like a ton of mining hardware and decides to sort of steal all the funds by just putting in some block where all the funds are transferred illegally to that government's address, and then it basically outruns in terms of chain length all the others. So that's not an infinite cost. It's a there's some finite amount of dollars that will give you that, but still, I treat it as such.
Cool. I can read one more question out if you want. Just while we still have a little bit of time. Jeremy Clark has a question that says, what evidence do we have on the concrete prover time for a ZK rollup? Correct me if I'm wrong, but assume there are 100 nodes. Validating a block of transactions on normal Ethereum takes W work. the NZK rollups pay for themselves when the prover work is less than 100 times the work. I assume there is some number other than 100 when ZK rollups start paying for themselves. Any sense of what that number is? So I guess what he means is, when does it become profitable to use a ZK rollup versus just sending it on the underlying chain?
Well, for us, the answer today can be converted to just US dollars. And what do I mean? I mean that if you, take DYDX right now. So as we're speaking, DYDX is now running, just DYDX is running at a rate of roughly 10 TPS. It's been doing so over the past couple of days, and this TPS is increasing. Now, each DYDX transaction is quite complicated because you have these collateralized multi-positions. So it would be roughly something like 4 ERC20s, trades. So this is like 4 or 5 times the TPS that Ethereum could support right now. Now, if you would have put that computation on Ethereum, the gas cost today, like the daily gas cost of Ethereum is around, I think, $1.2 million, the daily cost. If you put all this load on it, it would, of course, jump up to basically, everything would get clogged, but it would jump up considerably, 2x, 4x. We are putting these proofs at a cost on Ethereum that is 1/500 of that, like 1/5 of a percent of the daily cost in gas. And this cost in gas drastically, I'd say by a factor of roughly 10x, is bigger than the cloud cost that we have for the prover. So you're right that at some point, proving costs may be similar to or higher than what you pay on chain, but right now it's the other way around by a very large margin.
Cool. I think one thing you could highlight as well is like the difference here is that in native replay, the verifier has to re-execute every transaction, where in something like StarkNet, they only check the proof, and then they're given a list of state updates, they update the database. So you're not actually processing every transaction, you're just updating the values in the database.
Right. Yep. Yeah, and by the way, there's that's if you do it full roll-up mode, but past experience with the a lot of our customers, they said they want to do roll-up, but when they saw that they can also work with Validium, which means that you have a data availability committee and you don't put the data on chain, they preferred for their customers to do it that way. So what it means is that some customers are probably going to prefer to take the trade-off of slightly lower security, at least temporarily, because the data will be off-chain, and pay the lower costs of that. So you can even scale things a little bit further and just have the verifiers verifying the proofs and not even the data diffs,
Awesome. Okay, well, let's leave it there. Then we'll move on with Stephen. But thank you very much, Eli. Enjoy your holiday today.
Thank you. I'm running off to a holiday here in Israel. Okay, bye.